Good afternoon to one and all present here. It's my honor to introduce our today's chief guest, Dr.L. Jyothish Kumar, founder and president, Additive Manufacturing Society of India, Bangalore. He gained a Bachelor of Engineering in Mechanical Engineering from the National Institute of Engineering, Mysore, and Master's degree in Rapid Product Development from De Montfort University, United Kingdom, and completed his PhD research in aerospace applications of additive manufacturing technologies and advanced metallic materials. Prior to that, he has served in the mechanical engineering industries, different disciplines such as quality assurance, marketing, sales, and product development in India and abroad. He has specialized experience in quality management systems and rapid product development. He brings credible experience and knowledge from his project work at RPMG UK, association with other high-scale European Union funded projects with 33 other partners across Europe, including Delcam UK, Materialise Belgium, and Ducati Italy, developing a new rapid prototyping process based on combination of laser printing and infrared sintering polymers. He has signed a lot of MOUs across the world. He is member of editorial board of International Journal of Rapid Manufacturing USA and International Journal 3D Printing and Additive Manufacturing USA. He published a lot of journals and conferences, also organized a lot of international conferences. He also committed himself in social service activities. He is founder and president of Jeevan Jyoti Rural Development Trust, Mysore. It is a non-profit organization. It was started with the idea of bringing about a rural transformation, and it has involved in all aspects of rural life, education, health, environment, agriculture, women empowerment, and rural entrepreneurship. At present, the organization focuses the development of this rural human force through educating the children, providing the job oriented to the training to youths, empowering women, and spreading the awareness about health and environment. With these few words, I heartily welcome our Honorable Chief Guest, Dr. L. Jyothish Kumar. Thank you, sir.
Introduction. Hello.
Yes, sir. Audible, sir.
Is it audible?
Yes, sir. Audible. Also visible your PowerPoint, sir.
Visible. Okay. Okay. Thank you very much for the introduction. I hope we can start now. The
Yes,
PPT,
sir. Please.
is the PPT visible?
Yes, sir. Visible, sir.
Okay. Very good. Very good. So I hope this one. No? Okay. Good. Hello. Yeah. So I hope Dr. N. Shivaraman and his colleagues they have given brief introduction about myself. So let's not waste time because it's already 2:30. We'll start the session. So today I'm going to talk about advanced metal additive manufacturing processes and materials for aerospace applications. Okay. So is it my PPT is visible to all?
Yes, sir. Visible, sir. Visible.
Yeah. Yeah. So I would like to give a brief introduction about our organization, Additive Manufacturing Society of India. Okay, it is the leading professional body in India which is engaged in promotion of 3D printing and additive manufacturing technology in India. We have a lot of collaborations with international additive manufacturing organizations to promote R&D and manufacturing and training and skill development activities, particularly in 3D printing technology. And thereby we are contributing to empower India's advanced manufacturing technology in different sectors such as aerospace, automotive, defense, biomedical, health sector, and so on. So we also have a center of excellence, Additive Manufacturing Center of Excellence, which is focused on training industry professionals, engineers, students by catering R&D projects for various sectors such as defense, engineering industries, and R&D institutions as well. Also, we publish a journal called AM Journal and also a magazine, AM Magazine. So, which is the only magazine in India which we publish under AMSI name. Okay, and some of the key dates which we, which shows the milestones of our organization. The association is formed in 2008, and from there we have organized successfully 9th International Conference. In fact, this September we had organized 10th international conference, but due to the pandemic, we had to postpone it to next year. And this 10th international conference, which is a special edition for our organization and for our country, so which will be held during 2021 from 22nd to 23rd of September. This is the advisory board. Some of the dignitaries in the advisory board, starting from the industry professionals as well as bureaucrats and IIT professors and foreign research and development organization professors and foreign university professors, all involved in the advisory board. Yeah, this is our Center of Excellence in Bangalore. Hello, is it audible from my side?
Yes, sir. Yes, sir. Audible, sir.
Audible, okay. And the PPT is also visible, right?
Yes, sir. Visible, sir.
Okay, that's fine. Yeah, and we also have a MOU with the International Additive Manufacturing and 3D Printing Associations. This is one of the latest one which we formed, MOU and signed an MOU with 3D printing, Asian 3D Printing Union, which is in Korea, and we organize annual event in Korea. And I am representing Additive Manufacturing Society of India and the whole community of 3D printing sectors from India. And some of the MOUs which were signed with the French Rapid Prototyping Association and CMRD, Central Metallurgical Research Development Institute, Egypt, and MOU with German Consulate in India, where we are focusing on 3D printing and research activities, especially for defense, aerospace, and academic R&D segments. And we also have a MOU with British Deputy High Commission in India, so to focus on various research projects related to 3D printing. Yeah, this is a brief introduction about our association and organization. And now I'll just touch upon basic introduction of what is 3D printing and additive manufacturing before I get into the latest metal additive manufacturing and applications. We all know that additive manufacturing is a layer by layer fabrication of three-dimensional objects directly from a 3D CAD data. Okay, once we give the 3D CAD data to any additive manufacturing machine, it could be plastic, metal, ceramics, or biomaterials. It starts printing the object in 3D form by adding material in layers. We all know that it's also known by many names such as 3D printing, layer manufacturing, rapid prototyping, advanced manufacturing, free-form fabrication, solid free-form fabrication, direct digital manufacturing, and so on. And as for the ASTM International, and there is a body which controls and sets standards for additive manufacturing or 3D printing. It's called as ASTM International. ASTM International controls the 3D printing technology, terminologies, and the standards. And as for ASTM and ISO International, the official industry terminology for the technology is additive manufacturing. So that is the official terminology which we used for 3D printing is additive manufacturing. So as we know that there are three types of additive manufacturing processes, such as liquid based. When I say liquid based, there are various types of technologies because the raw material will be in a liquid form, such as SLS stereolithography apparatus, then polyjet printing, which is called also multi-jet printing. So where the raw material will be in a liquid form and laser cures the liquid material and converts that into a solid object. Then the solid based process is called as FDM fused deposition modeling, where the raw material will be in the solid form, that is in the form of a wire. Then the powder based. In powder based, we have two types, that is one for plastic and for metal as well. That is for powder based additive manufacturing is SLS, selective laser sintering, where the raw material will be duraform, that is a nylon powder. And in case of metal, the process is called DMLS, direct metal laser sintering, and also LMD, laser metal deposition. These two processes uses the powder-based metal powder to fuse and form an object into a solid object by adding the metal powder layer by layer. Then another process is called EBAM, electron beam additive manufacturing, which is also called as wire-fed metal additive manufacturing process. where the raw material will be the metal powder is not used here. Instead of metal powder, the wire fed, the metal powder will be in the form of a wire, and that will be fed to the machine, and the high powered electron beam melts the metal wire and forms the object layer by layer by adding a material onto the object as per the CAD data. These two are the latest developments in additive manufacturing, and there are wide applications of these two processes in all the sectors such as aerospace, automotive, defense, space, and so on, because of the versatility of these two processes and the availability of multi-material options. So we can use n number of materials in these two metal processes, and which has got wide applications in key sectors. So I'm going to explain about LMD in my coming slides. Yeah, I'm going to take one of the case study where we have used live case study for HAL engine division. I think I can share this because I got a permission to share this PPT, and we have done a fantastic research for HAL Hindustan Aeronautics Limited. And the process what we used here is a laser metal deposition process. As you know that laser metal deposition is a blown powder additive manufacturing process. When I say blown powder, the powder is blown into the platform, and the high power laser melts the powder and forms the object layer by layer based on the CAD structure or the CAD data. So thereby the raw material is fed to the building chamber, and the laser melts, cures and solidifies and builds the object layer by layer from bottom till top. And here the high powered 2.5 kilowatt fiber optic and CO2 lasers are used, which is powerful laser to melt the metal powder. And there are various types of metal powders which we can use here. That is merging steel, stainless steel, low carbon steel. Then Inconel, in Inconel there are various types of Inconel, Inconel 625, Inconel 709, and so on. And there's a latest material called Marem. Marem is the lightweight material which is used for aerospace applications, and also cobalt, chrome, titanium, highly precious and important metal alloy for aerospace applications, and tungsten carbides, and even the copper can also be used. The latest developments here is the copper powder can also be used to make components using this process. The best important thing is that the metallurgical bonding. When we sinter or fuse or melt in any metal additive manufacturing process, what we see, the final end result is the bonding between the layers and to get a dense parts, right? So once the bonding is good, then our solid part or the end part will be good for end use applications. If there is no good metallurgical bonding between the layers, then there's of no use in fusing or melting the powders. So the research shows that the metallurgical bonding is very good between the layers and the part is completely dense. Yeah, another applications of this LMD process is that it forms repair applications as well as build components from the CAD data. When I say repair applications, for example, the existing component which is damaged or which is worn out, when we see the aerospace components, 90% of the components will be replaced after a certain amount of cycle time. So these parts are being thrown or they're discarded because of there is no facilities available to repair the components and put it back to the engine for further use. So the LMD process gives very good uh, applications in repairing the components. So we can repair, we can deposit the same material or even the better than the base material to
ये
achieve
इंडियन होगा
the required results and to use for further applications. As you can see, some of the applications of LMD, some of the critical aero engine parts which have been built using laser metal depositions are these critical aero engine applications parts. And as you can see here at the right side, we can also use LMD process to make components in functionally graded metals, FGMs. FGM is a material where we can deposit, where we can use various types of materials in a single go. For example, as you can see this picture, My base material is Inconel 625. And on top of that, we have deposited Hennes 230. And again, on top of that, we have deposited Hennes 230. On top of that, we have deposited Inconel 718. On top of that, we have deposited Inconel 718. But the latest applications shows that we can also deposit Ti6L4, that is titanium, aluminum, and vanadium. We can deposit on top of the Inconel 718 structure. So this shows that we can use LMD process for functionally graded material applications. I would like to show the video of LMD just for a better understanding of the process.
LDT, which stands for Laser Deposition Technology, is an additive process that is used to build freeform fabrications. Repair metal components typically considered non-repairable by conventional techniques, or strategically add features to forgings or castings. All capabilities come directly from CAD data. No hard tooling changes are required. LDT deposits exhibit excellent material properties. These material properties, combined with the flexibility of the process, significantly lower overall production costs. When used for manufacturing and the production of prototypes, the LDT process greatly reduces product development time. First, a 3D CAD file is created that defines the component that is to be built. Next, the system software uses this file to slice the piece into numerous horizontal sections and then creates a toolpath for each layer. This toolpath is followed by the laser as the piece is created, layer by layer. The build takes place in a controlled environment chamber with less than 10 parts per million oxygen. Once the chamber is prepared, the build can begin. The laser fires and creates a melt pool on the surface of the target plate. A stream of powdered metal is delivered into the melt pool. When the powdered metal impacts the melt pool, it is absorbed into the melt pool and creates a weld bead. Fusing multiple layers together generates a 3D solid metallic build. A variety of alloys can be used in this process, including tool steels, stainless steels, nickel, cobalt, and titanium alloys. Deposit quality and consistency is of primary importance for all laser deposits. Weld beads are produced in a very low oxygen environment with a very small laser spot size and relatively high travel speeds. The laser deposits have extremely high cooling rates. These cooling rates generate a very small localized heat effect zone, thus minimizing distortion. Also, the high cooling rates result in laser deposits that have very fine microstructure. Therefore, the deposits typically have similar mechanical and physical properties compared to wrought products. LFMT, which stands for Laser Freeform Manufacturing Technology, possesses a unique ability to build parts with novel geometries from high-quality metal alloys and may transition to functionally gradient material compositions, opening the door for the production of breakthrough end products. Complex forgings and castings may be simplified and reduced in size, followed by the creative addition of specific features using the process. Substantial material and cost savings may be achieved using this novel combination of processes. Additional cost savings may be realized by the reduction of final machining time. Implementing design changes and new iterations for freeform builds is far simpler using this process than many traditional processes. Modifications are made in the CAD model, new toolpaths are generated, and a new version of the piece is deposited. LCT, which stands for Laser Cladding Technology, is also a very effective process for performing repairs on heat-sensitive materials, such as 4340 or pH-grade stainless steels. After the wear area is identified and a tool path is generated, the repair is initiated. By carefully controlling laser power and travel speeds, the heat effect and dilution zones are minimized. The result is a very low stress input into the part, which results in very low distortion. After a build is completed, the component is scanned using a portable CMM and scanning laser. The scanned file is compared to the original file to be certain no significant distortions have occurred and that enough material has been deposited to ensure cleanup during final machining. Minor discrepancies are carefully noted so that future potential distortions can be compensated for and therefore avoided. With laser deposition technology, potential applications are endless, and the advantages over traditional methods of creating small runs, prototypes, and performing repairs are substantial. Lower per-piece production costs, lower upfront tooling costs, and greatly decreased development time represent significant savings in time and money. Enhanced design flexibility leads to better products. Superior material properties provide longer product life, and the process can create products and repairs that are impossible using current traditional methods. For answers to your questions about specific applications, contact RPM Innovations Incorporated, 605-348-0555, or visit them on the web at rpm-innovations.com.
Yeah, that video shows about laser metal deposition process, which is an advanced 3D metal printing process where we can use the technology for free-form fabrication, as that means to build a component as a new component or to repair the existing component. Yeah. So the material, the laser metal technology, LMD, uses various types of materials. Especially for this case study, we have used Ti6L4V, that is a titanium, aluminum, and 4 vanadium. So as you all know that the properties of the Ti6L4V, which has got alloy with 4 vanadium, 6 aluminum elements with a symbol of Ti, atomic number 22, then Ti-S6L used for various aerospace applications due to some of the interesting properties, that is of lightweight, as a low density, which is of that steel. That means the part which is built of LMD using Ti6L4V is having a very lightweight and having high melting point and high strength. So these are very critical, important aspects for aerospace applications, whereas the aero structure or the aero engine part has to take care the load. That should take care of the load at higher speed, and also at the same time it should not contribute the higher ratio weightage of the structure or the part, because that thereby it reduces the fuel consumption of the aero engine. So this is the perfect material for aero engine applications in terms of structures or in terms of engine components. So Ti6L4V 6L4V is a very good alloy for aero engine applications, and most of the components are being made or being built using this material. And LMD is the best process. Why? Because Ti6L4V itself is a very expensive alloy, and the machining of this alloy is very difficult and it's a very tedious process, and we are not afford to waste the Ti6L4V by removing the material. So LMD or the 3D printing process is the best process where there will be minimal material wastage, and we can get a better part in terms of the weight and the bonding and for various applications. And some of the applications of Ti6L4V, or especially in aerospace, these components are used in airframe structures, in aero engine parts such as compressor blades, vanes, discs, and so on, because it withstands high temperature and having high strength to weight ratio. That is, it can withstand high temperature. At the same time, the weight of the component is very less. Yeah. The case study what we have done is for HAL engine division is the repairing of axial compressor blade. There's an actual case study which we have taken for the study. This is the blade. This axial compressor blade from this helicopter engine. Yeah. So this engine is called as Autost 3B engine. So there are various types of engines in defense. So this engine, what we selected for the study is Autost 3B engine. And in this complete engine, we have selected the axial compressor blade, which is a very critical component. Okay, so we selected this component for the study. Initially, these components are being once after a certain time of after certain what you call as a lifetime of the part, they used to throw these components because of there are various factors contributing to the failure of the components, such as high temperature. The engine runs at high temperature, and external bodies hit the engine, such as dust or other factors contributing to the damage of the engine components. Even the edge, if the edge is damaged, so they were throwing out the component, and they used to replace, then they used to bring down the engine and make a new component, and it used to take more time, and it was very expensive as well. Then we gave this suggestion to HAL engine division, so why don't we try repairing the existing component with LMD process. Then they have given approval, and we did a lot of paperwork to take this component for studies. So as you can see in the picture, this is the component which we taken from this engine. This is the cross section of the engine of Autos 3B. Yeah. So repairing of axial compressor blades. There are various types of failure occurrences on axial compressor blades, because when we say axial compressor blade failure, the blades faces various types of load, such as impacts during high fatigue cycle, failures, and wear and cracks at the leading edge. There will be two ends in any axial compressor blades. Okay, one is the leading edge. Okay, so the leading edge is the one which faces the most uh, failure occurrences of the chances due to wear and tear and cracks at higher speed. As you can see in this image, the worn out portion of the engine, which shows that the engine component, the axial compressor blade, is not ready to use for further use. That means we have to replace this. If you continue to use this, then it will cause a catastrophic failure of the entire aircraft. So once we see these, what do you call as worn out parts or the dents on the leading edges, we have to replace the engine component. Yeah. So initially we did failure investigations, like how fail, what is the mode of failure? Is there only at the leading edge, or is there the failure at the inside of the axial compressor blade? Then we did NDT using ultrasonic flaw detector liquid penetration test and eddy current examination to detect the surface flaws. But the investigations revealed there were no surface irregularities. However, by seeing the, by visual inspection revealed that there are some dents at the leading edge where the air enters to the engine. There we found some dents and some worn out portions. Yeah. So then we taken the component for building or repairing using LMD process. As you can, this entire setup, how we have made a fixture to repair the axial compressor blade. Yeah. So we found two locations at the leading edge. Another one is just opposite to the leading edge. So initially we did a lot of preparations before depositing. So any blade or any part which is going for repairing using laser metal deposition, metal additive process has to be cleaned with the different types of solutions. So we used NovaClean 909 and acetone because to remove the foreign objects such as oil, dents, and any other dust deposited on the surface before the deposition. After cleaning, we have taken that into a controlled organ chamber, because it's very important to have a controlled organ chamber in LMD process, because to avoid oxidation. Yeah. And some of the technical informations where we have used 5 gram per minute. Before this, we did a lot of characterization studies and process optimization uh, of LMD process to specifically and finally deposit the material on the worn out portion. So these are some of the parameters where we use around 2650 watt power and 5 gram per minute of the feed rate and 700 mm per minute of the scan speed of the laser on top of the depositing layer, and with a thickness of 0.6 mm and 3 mm beam diameter. As you can see, this axial compressor blade has been deposited. The process, this shows it's being deposited, and this area shows the deposited portion, and this area, the highlighted area, clearly shows the blade worn out portion has been successfully deposited. Yeah. After deposition, we did a lot of studies, such as microstructure studies. After deposition, we did the cross section of the the blade, and we have studied for various types of studies, microstructure studies. And before microstructure studies, we had to do a lot of preparations, such as we have to clean the surface to have a very good visibility of the microstructure inner portion of the deposition. Okay, then we did optical microscope to study the metallurgical bonding between the layers after the deposition with the base material. This image shows the axial compressor blade which is being sectioned after deposition. Yeah, the microstructure results. Basically, the Ti6L 4-way alloy represents fine Widman-Staten structure. The fine Widman-Staten structure with the acicular alpha structure phase in the interface zone. When I say interface zone, that is the zone where the deposited material is bonding properly with the base material. Okay, if we observe Widman-Staten structure, then that shows that the bonding between the base material is very good, and which also reveals that the metallurgical bonding with the substrate material is very good, and there is less heat affected zone. Okay, as you can see, this is the dense deposit area without surface cracks. There's also the complete dense deposited area without cracks, without pores. And this is the substrate portion. When I say substrate, substrate is the base material, that is the blade, where we have deposited the same material. Yeah, and this image clearly shows the Widman-Staten structure with the deposit, the interface, and the substrate. It's completely looks like as a single material with the clear Widman-Staten structure, where the deposited material is completely bonded with the base material. Right? This is the interface where you cannot differentiate the interface line between the deposited material as well as the base material, which you call it as a substrate. So this is an evident factor saying that LMD process is very good for repairing of any existing components. And this structure shows that acicular alpha phase. That means the bonding between the layer is very good. Yeah. Also, we studied for the micro hardness. The micro hardness is a very important factor. Once we deposit any material to the base material, we have to test the hardness, micro hardness. As you can see this, the table, the deposited material and the substrate showing almost the same values in terms of micro hardness distribution, which shows that the deposited material has bonded completely with the base material. Yeah. Again, we have studied the microstructure of the bonding material on the deposited material at two locations. The initial one, what we seen at the location 1, again we have sectioned the deposited material with the base material of the axial compressor blade, and we have studied for the microstructure at the location 2, where it shows the complete bonding between the layers. Again, we did all the process of cleaning the surface for microstructure analysis. and all those initial preparations were made as per the ASTM standards. Then we have studied which shows the cross section of the compressor blade with clear uh, bonding between the base material on the deposition. Yeah, this is the structure. This is the cross section view of the blade, and this is the microstructure result. This microstructure results reveals again the fine Widman-Straiten structure. Widman-Straiten structure is a very important phenomenon of any Ti6L4V alloy. As you can see, this the fine deposited area with the base material, and this is the interface line. So the bonding between the base material with the deposition is completely dense and clear. There are no pores and no cracks, which clearly shows that the deposition is successful for repair applications. Yeah. Later on, we also studied for the porosity. Porosity is a very critical factor of any engine components when we deposit using any additive manufacturing process, such as blown powder, or it could be a powder bed for fusion. The porosity contributes a lot in terms of controlling the strength of the component, and we should have minimum porosity to have a better structure or the better bonding and the better strength of the component. And as you can see, this obviously there are no porosity, and it shows that the clear bonding between the layers, and the deposition is dense and completely solid. Yeah, and some of the data have been plotted, and it shows that the bonding is very good. Then the interface shows a very good result of porosity and hardness, which is almost closer to the bonding between the base material and the deposition. That is evident that the deposited material is completely melted with the base material, showing very good strength of the repaired blade. Yeah. So the conclusion part of the axial compressor blade, the repair, what we observed, says that the repaired I6L4V axial compressor blade revealed a fine Widman-Straiten structure, which is on par with the literature search as well as the basic metal structure of the Ti6L4V alloy. And it also shown the sound deposition with good interfacial bonding between the deposit and the substrate without lack of fusion or cracks. That is very important factor, because I also showed in my previous microstructure, the bonding between the material and the deposition was very good without no pores, cracks, whatever it is. And it was completely dense deposition. Yeah. And the porosity level in the deposit was also very low in both deposit and the interface zone, and with the acceptable limit. Yeah, there are certain limits of porosity where you can accept, and up to 1%, 2% porosity is there that you can accept. Okay, so the deposition process was done within the acceptable limit, and the porosity level was very, very low, and it was in the acceptable limit for different applications. And finally, the result shows the laser metal deposition is a potential process to repair critical high value aero engine components with reduced cost and time. When I say high value aero engine components, titanium alloys are very precious, and we cannot waste even a gram of material. You cannot machine and waste the material. So this is a high value component, because a lot of cost involved in making the component as well as procuring the Ti6L4 alloy itself. So in case of LMD, what happens? We will not be machining, will not be wasting the material, but instead we'll be adding the material with a minimal wastage of the powder, Okay, so this helps us to reduce the cost and preparing the critical components such as the blade, axial compressor blade, which you have seen. And we successfully developed this process and repaired the component, and gave this to HL engine division. And now this component is being used in the same present engine. And it was a successful project with reduced cost and lead time. It took us only 4 days to repair the blade and put it back into the engine and start the engine. Okay, otherwise it would have taken months together to make the same blade by forging or any other processes. So that shows that, it has reduced the cost and the cost of time. We have a small announcement. We are coming up with the 10th International Conference during 2nd to 24th of September 2021. Hopefully, the pandemic, will take a break during that time. With all these factors keeping in mind, we have scheduled our 10th International Conference in Bangalore at BIEC. And for more details, please contact. You can also send papers. Research scholars or professors who would like to be part of this event, they're most welcome. For details, you can visit our website. Okay, thank you very much. And any doubts, I can take a couple of questions before ending my presentation. Thank you. Hello.
Sir?
Hello.
Yes, sir. Audible, sir.
Yeah.
Participants, if you are having any questions, kindly post in the chat box, or you can unmute from your mobile and ask the queries to our resource person. Sir, can you brief about to join as a member in your association? What's that process? Can you little bit share?
What you can do, we have a membership form. You can send us an email at my email ID jyotish@amsi, or contact us at amsi.org.in.
Okay.
Or you can log into our website.
Okay.
Okay. So there's a membership form. You have to fill it out and send the details. And there is a certain amount of membership fees.
Okay.
Yeah.
It should be of a life member or year wise, sir.
Yeah, there are various types of memberships. For industry, we have a different membership, and for professionals and academicians, we have a different membership category. Lifetime membership is there, and annual membership is there for industries. You can visit our website. All the details are there.
Yes, sir. Yes, sir. Yes,
yeah.
Sir.
Yeah, this is Dr. Mohandas from Sivaganga College of Engineering, Mr. Jyothish Kumar.
Yeah, tell me.
Yeah, very nice presentation. And just I want to know, the AMISI, the international conference, will be conducted in online mode or offline, sir?
No, actually, we don't do online because it is a touch and feel effect. Because there will be a lot of what do you call it as we parallelly have exhibition as well, conference as well as exhibition. So in the exhibition, there will be display of components, display of materials, display of machines, display of softwares from across the world. Okay. So that's why we had to cancel this year's conference because there is no point in doing without touching. You won't understand, and the concept. Yeah.
So the venue will be in Bangalore itself, sir.
Bangalore, yeah. Hello. Yeah, the touch and feel is very important factor in manufacturing process. It's not like any other software forum or the software, process. You have to see that component, you have to see that machine, you have to feel that. Then only you will be able to understand in a better way. Yeah. Any other questions, please?
Sir, are you conducted any type of any skill training programs relevant to that additive manufacturing, sir?
Yeah, we have been doing it. And from past, 8 months, we have been not able to do it because of the pandemic.
Okay.
And again, we are going to start from next year onwards, hopefully, after after this vaccination program is implemented. Yeah.
Whether it should be a short-time program or a house, sir?
Yeah, we do short-term programs like 15 days, 1 week.
Okay.
Yeah.
Okay.
Sir, good evening, sir. Myself, I am Dr. V. Armu Prabhu. I am audible, sir.
Yeah, very much.
Yeah, sir. May I know any kind of training program you are organizing for the students, sir, related to this additive manufacturing?
Yeah, we have been doing it. As
Okay,
I told
okay.
we have been doing it. We have been doing it, and we have done a lot of successful programs for students, especially for MTech students, and we have given projects also. And they have done successfully all these projects in 3D printing, and they got their degrees as well, and most of them got placed through a reference.
Okay, sir. Okay, sir. Thank you very much, sir. I will contact you through your mail or
Please,
mobile later
please,
on, sir. Say, sir.
please,
Thank you,
yeah.
sir.
Yeah. Any other questions, please, from the audience related to the LMD process and blade repair?
Participants, if you have any queries, you can ask.
Or if you have any
Or you
doubts, you
can
can
post
also
in.
you can send me an email also, or you can call me later on also if you get any doubts. But if any faculty members would like to do their PhD in the latest additive manufacturing process such as EBM and LMD, you are most welcome. You can contact me. I can suggest whatever I got the information. And it's a very good R&D field. You can try various types of materials for various applications. And a very good PhD subject. A lot of
One second,
innovations.
this is Mohan Das. Just I would like to know what kind of.
Hello.
On the sir, not audible, sir.
Excuse me, sir.
Hello.
Udhay Kumar, sir, my
Yes.
voice is clear?
Yes, sir.
Because
Now
I'm
clear.
not getting clear audio from
Sir,
anybody.
voice is clear, sir. You can come talk, sir. You can talk.
Hello, sir.
Yeah,
Yes.
please.
Udhay Kumar, sir.
Yes, sir. Audible, sir. Audible, sir. You please.
Oh, okay. I'm not getting the clear voice from Dr.
Yeah, I can hear you. Please go ahead. Hello. I can hear you. I can hear you. Please go ahead.
Okay, sir.
Hello.
Sir, are you?
Sir.
Yeah, I'm able to hear you. Please go ahead.
Maybe some.
Sir,
I'm not able to.
Sir, post.
Hear the.
Sir, are you post your query in the chat box too, sir?
No problem. Please.
Sure, sir. Sure. Yeah.
Yes, please.
Any other questions from the participants, please?
Sabri, sir?
Yes, sir.
If no questions, you can summarize and conclude the session, sir.
Okay, sir. Okay.
Yes,
Sir,
sir.
Mohan
Das, sir, ask the question, sir. Sir, Jyothish, sir? Jyothish, sir?
Yeah, please. Yeah.
That Mohan Das, sir, asked the question that what methodology used for finding delamination of 3D printed components?
Delamination. What
Yes.
we can do the bonding strength.
Okay.
Yeah, bonding strength test is the best method to see the delamination
That's
process.
a delamination of the layers, sir. Actually.
Yeah. That is a bonding strength. Bonding strength, you can use that. There is a tensile strength.
Okay, Sabri, sir?
Yes, sir.
Yes, sir. Please.
So thank you, Dr.L. Jyothish Kumar, sir, for your wonderful presentation about your association, and you explained the latest additive manufacturing processes for aerospace applications. The video was also very impressive, sir. And you also invited us for your conference in 2021. Definitely, I hope that many participants will submit the papers in your conference, sir. Thank you very much, sir, for being part of this FDP adult program and sparing your valuable time for this FDP, sir. On behalf of Department of Mechanical Engineering, K.L.N. College of Engineering, we thank you, sir, for your wonderful lecture in this afternoon, sir. Thank you, sir.
Thank you very much. Thank you very much. Thank you for inviting me. Yeah. Good day.
Thank you, sir.
Thank you.
Thank you.
Thank you.
Thank you. Sir, dear participants, kindly fill up the feedback form for this today's sessions. So tomorrow we have invited 3 resource persons, fully of academical person. The first session is from Tuskar Bera, professor from the Department of EEE, NIT, Durgapur, West Bengal. The second session is going to handle by Dr. S. Vinod, professor from the Department of Production Engineering, NIT Tiruchirappalli, is going to take the 3D printing and sustainable manufacturing. And tomorrow's afternoon session is going to handle by Dr. Rajesh Ranganathan, professor, mechanical engineering from Coimbatore Institute of Technology, Coimbatore. He is going to deliver the applications of research in 3D printing. So fully tomorrow's sessions is fully focused on that academicians, right? So the next day, that is the Friday, the first session will be of the demonstration of 3D printing and 3D scanners. And after that, the 14th session will be of the life management skills, that stress management. It is full of non-technical. It should be opted by the Atal Academy, has asked you to do some one non-technical session as stress management. So Friday afternoon, we have an online test that should be covered for that 13 sessions. It might be of MCQ questions. 25 questions will be given. It should be in the form of Google Forms, right? So the certificate will come to you in your login ID with the eligibility of 80% of attendance in this FDP, as well as 60% of marks in that online test. Right, the last session will be of online test and group photo session, feedback session, as well as that valedictory function. So Friday afternoon, the session will be comprises of things. There is no technical lecture, right? So we have to update whatever the things then and there. So I once again request if anybody having any clarifications or any queries or any problems faced during posting that feedback, kindly inform to us. Our team will ready to helping you to sort out your problems. Right. Also, once again, I remind that we will share the link of all the session videos to all. So if you are having any queries, please unmute and please ask. Sir, any queries or any discussion from the participants? Sir, most welcome. So kindly be interact with this. Now, sir, you can close the recording, sir.
Okay, sir. Okay, sir.